Hey everyone. So, today we're diving into a material that's basically changing the game in everything from Formula One cars to the jets we fly in. I mean, it's a total icon of high performance, right? It feels like something straight out of science fiction. But here's the thing, this superhero material has a secret, a kind of hidden side that we're going to uncover together. Okay, so let me just start with a quick question for you. What pops into your head when you think of something that's stronger than steel, but at the same time, it's lighter than plastic? Seriously, it's so light, it almost feels like plastic in your hand. It's a bit of a riddle, yeah? But the answer is at the core of so much modern engineering. Any ideas? You guessed it. It's carbon fiber. And its magic, it's not just one thing. It's this perfect storm of three amazing properties. First up, you've got its tensile strength. That's basically how well it resists being pulled apart. And it is absolutely staggering. We're talking something like 10 times stronger than the same weight of steel. Then you've got its high stiffness. It just doesn't bend or warp easily under pressure, which, as you can imagine, is crucial for things like airplane wings or a race car's body. And the third piece of the puzzle? It does all of this while being incredibly lightweight because of its super low density. It's this unique combo that makes it the absolute go-to material whenever performance is the name of the game. But here's the catch. You can't just, dig carbon fiber out of the ground. No way. It has to be made through this incredibly precise, super demanding process. And if we really want to get what makes it so special, we've got to look at the intense, almost alchemical journey it goes through. It is, and I mean this literally, forged in fire. So it all kicks off with something called a precursor. Just think of it like the raw ingredient, the thread that's going to become our super material. Now, the most common one, and we're talking for over 90% of all carbon fiber made, is a polymer called polyacrylonitrile, or just PAN for short. So they take these long molecule chains and spin them into these unbelievably thin filaments, way, way thinner than a human hair. And once they have those, they're ready to get cooked in one of the most intense processes you can imagine. All right, so the whole creation process is this multi-step journey. After the spinning we just talked about, the fibers go through a wild two-stage heating process. First carbonization, then graphitization. I mean, this is where the real magic happens. It basically burns off everything that isn't pure carbon. After that fiery purification, the fibers get a special surface treatment so they can stick to other materials. And then finally, they get a protective coating called sizing. Let's zoom in on that heating part for a sec. Okay, so this is super interesting. You've got carbonization and graphitization. They're both about heat, but they do totally different things. Carbonization comes first. And when I say lower temperature, we're still talking a crazy 600 to 1200 degrees Celsius. In that furnace, all the junk, the non-carbon atoms like hydrogen and nitrogen, they just get baked right out. What you're left with is what we call high-strength or HS carbon fiber. But if you want the really top-tier stuff, you have to crank that heat way, way up. That's graphitization. We're talking blistering temperatures, anywhere from 1600 up to 3000 degrees Celsius. It's so hot that the carbon atoms themselves start to line up in this super ordered, perfectly packed crystal structure. And that perfect alignment is what gives you the incredible stiffness of high modulus and ultra high modulus fibers. The hotter you go, the more perfect the alignment and the stiffer the fiber. So the very last step before these fibers are ready for the world is called sizing. Now, you've got to remember, these individual carbon filaments are super fine and honestly pretty fragile to handle on their own. Sizing is basically a thin protective coating, usually an epoxy resin, that gets applied. It does two really important jobs. First, it bundles all those thousands of tiny filaments together and protects them from getting damaged when they're being woven into a fabric. And second, and this is absolutely key, it acts like a chemical matchmaker or a bridge, making sure the fiber can form a really strong bond with whatever resin it's going to be mixed with later. See, without sizing, you've just got a bunch of strong threads. With sizing, you've got the building block for a seriously tough composite material. Okay, so we've got this incredible, mind-blowing material. It sounds perfect, right? Well, remember that secret I mentioned at the start? This is it. The process of creating something so strong and so pure in those fiery furnaces, it comes with a massive price tag. And I'm not talking about money. I'm talking about the cost to our planet. Let's just start with the raw energy. Look at this number. 900 megajoules. That's the energy it can take to make just 1 kilogram of carbon fiber. To put that into perspective for you, that's about the same amount of energy an average American home burns through in 2.5 days. All of that just to make a couple of pounds of this material. And almost all of that energy is just to get those furnaces hot enough for carbonization and graphization. And where there's that much energy, there are emissions. This chart just lays it out so clearly. Making 1 kilogram of steel, which is not exactly a green process itself, pumps out about 2.1 kilograms of CO2. Now look at carbon fiber, almost 25 kilograms. That's not a little more, that's over 11 times higher. It's not even in the same ballpark. So you've got this crazy situation where a carbon fiber part might make a car lighter and more efficient over its lifetime, but the process of just creating that part leaves behind a massive carbon footprint. But that's not where the story ends. Of course not. These huge challenges, making it stronger and making it greener, are pushing some really incredible innovation. Scientists aren't just sitting back. They're not satisfied. They're actually working at the microscopic level to push the boundaries, make it even stronger, and maybe most importantly, fix its weak spots. Okay, so here's the fundamental challenge. The final strength of a part made from carbon fiber isn't just about how strong the fiber is. It's really all about how well that fiber grips the resin it's embedded in. If that bond is weak, the whole thing will just fall apart under stress. And the problem is, a freshly made carbon fiber is actually really smooth and chemically, well, kind of boring. The resin just doesn't have anything to grab onto. It's like trying to glue two perfectly smooth pieces of glass together. It's just not going to hold. So what do? You've got to modify that surface. And a solution is to use all sorts of different surface treatments. The best way to think about it is like sanding a piece of wood before you paint it, right? You're roughing it up to give the paint something to stick to. It's the exact same idea here, just on a crazy microscopic scale. Things like plasma treatments actually etch the fiber, creating all these little microscopic grooves and nooks and crannies. This creates what engineers call a mechanical interlock, which is just a fancy way of saying it gives the resin a ton of tiny hooks to grab onto. But it gets even cooler than just roughing it up. These treatments don't just change the physical texture, they also change the surface chemistry. They add these oxygen-rich groups onto the carbon surface. You can think of them as tiny chemical handles, or even like microscopic Velcro hooks that are just waiting to form super strong chemical bonds with the resin. So you end up getting the best of both worlds. You get a better physical grip and a much stronger chemical bond. It's this 1-2 punch that makes a massive difference in how well everything holds together and how strong the final part is. Which brings us to the big question about the future. After everything we've talked about with the environmental cost, the number one question for the whole industry is pretty simple. Can we make this superhero material without wrecking the planet? Well, the good news is a lot of research is pointing towards a much greener future, and it's really moving forward on two main fronts. Okay, so path number one is all about finding sustainable starting materials, those precursors. Instead of using PAN, which comes from fossil fuels, researchers are looking at things like lignin. Lignin is basically the natural glue that makes trees and plants rigid and strong. And guess what? It's a massive waste product from the paper industry. So we could turn that waste into something amazing. Then there's path number two, creating a real circular economy for this stuff through better recycling. Right now, it's super hard to separate the fibers from the resin, but new techniques, like using microwaves to help with chemical recycling, are starting to show we can actually pull out high-quality long fibers from old parts. That means we can reuse them instead of just throwing them away. And all of this brings us right back to the core dilemma, doesn't it? For so long, it felt like you had to choose. You could have incredible performance, or you could have a healthy planet, but not both. But now, with breakthroughs like using lignin and creating a real circular economy for these materials, that choice is starting to look, well, a little outdated. The goal isn't just to make something stronger and lighter anymore. It's about making it smarter and more sustainable. So the real question now isn't just can we innovate our way out of this problem, but can we do it fast enough to really make a difference? Do we really have to choose? The future of materials might just hang on that answer.